Hello everyone, this is the video solution of June 22 Unit 2. Let's take a look at the very first question. Question says, a ray of light is incident on the boundary between two materials X and Y as shown. The refractive index value for material X is Nx and for material Y is Ny. Which row of the table gives the conditions required for total internal reflection to take place at this boundary? So from your IGCSE days, you should remember that total internal reflection takes place only when a material, when light is traveling from a more dense to a less dense medium. So in AS, more dense is associated with a material with higher refractive index, and less dense is associated with a material with a lower refractive index. So since light must be traveling from a more dense to a less dense medium, X has to be more dense, meaning X must have a higher refractive index. So Nx must be greater than Ny, and angle of incidence, that is the second requirement, is always greater than critical angle. So answer should be A. Now let's take a look at question 2. The graph shows how the displacement x of particles in a wave varies with time t. The speed of the wave is not known. Which of the following cannot be determined? So focus on not. Be determined from the graph of displacement against time for the particles in the wave. So this is displacement, and this part is the maximum displacement. So this part is the maximum displacement, so we can easily find out the amplitude. This is no problem with A. Frequency, you can actually, so this is the time period, and 1 by time period gives me the frequency, and period can be easily found out from here. What you cannot find out is the wavelength, because for wavelength you need to have the distance, and the distance is not given. So the question says cannot be found out, answer must be wavelength, that is D. Question 3 says, when the distance between Sun and the planet Mercury is 4.6 times 10 to the power 10, the intensity of solar radiation at the surface of Mercury is, the value is given. Which of the following expressions gives the power of the Sun? So answer is B, of course, and let me show you why the answer is B. It's better if I just draw the Sun and the Mercury. Let's say this is the Sun, and let's say this is Mercury. What's happening is Sun is shining light in this direction, as in all directions. Basically, it's creating a sphere of rays like this. So how do I find out intensity? When you have a point source. So here Sun is acting like a point source. So when you have a point source, the equation is intensity equals power divided by area. Now the area is area of the sphere, because it's shining the light spherically, and the area of a sphere is given by 4 pi r squared, and this r is the distance between Sun and the Mercury. So if you make power the subject of the equation, equals to intensity times 4 pi r squared. So this is the intensity, and here you have 4 pi, and this is the distance squared, or r squared. Question 4 says, a ray of unpolarized light is incident on a polarizing filter. The polarizing filter transmits light of intensity I as shown. Polarizing filter is then rotated in the direction shown on the diagram. Which of the following gives the intensity of light transmitted after the filter has been rotated? That's the thing. Please focus on this term, unpolarized. So when you have unpolarized light source here, as in oscillations are in multiple directions as well as multiple planes. And when it passes through a polarizing filter, of course the intensity decreases, but even after rotation the intensity doesn't vary because it's unpolarized. Had it been a polarized light source, and if you were to rotate the polarizing filter, this intensity would have varied between maximum and minimum after every 90-degree rotation. That's only for a polarized light source, but since it's an unpolarized light source, the intensity compared to over here will definitely decrease, but the rotation would not cause any change in intensity. So even after rotation, the intensity will still remain as I. So answer should be D. Question 5 says, a laser diffraction grating and screener setup as shown. The position of the central maximum is O and position of the first order maximum is X. So please focus on first order. So whenever you get a question associated with diffraction grating, always remember the equation is d sine theta equals n lambda. I don't even see what the question says. So let's see. Which of the following expressions gives the wavelength of the laser light? So answer is D, and let me explain why the answer is D. Like I said, every time you come across diffraction grating, just recall the equation d sine theta equals n lambda, and since the question says first order, the value of n will be 1. So therefore lambda is basically d sine theta. Okay, so how do I find out sine theta? If this is that angle, so sine theta is, this is opposite by hypotenuse. So opposite is 0.378. So lambda equals d into sine theta would be equal to opposite by hypotenuse 0.378 divided by hypotenuse is 2.035. Now all we're left with is d. What is this d, everybody? D is 1 by lines per millimeter, but if lambda has to be found out in meter, d has to be in meter, therefore we have to consider lines per meter. So 300 lines per millimeter is the same as 300,000 lines per meter. So d is 1 by 300,000 lines per meter. So lambda is given by 1 by 300,000 times 0.378 by 2.035. That's what makes my answer D. Question 6 says, at a point in a circuit there is a current of 3 ampere. Which of the following gives the total charge passing through this point in 2 minutes? It's a very clear case of the use of the equation Q equals IT. Value of I is in ampere, so no need for conversion, but this 2 minutes has to be converted to 2 times 60 seconds. So my answer is D. Question 7 says, the diagram shows an electron transition between two energy levels in a hydrogen atom. Which of the following could not have caused this transition? Okay, so let's focus on not. Answer is A, of course. Okay, so if I ask you, how does this transition occur? Of course, the electron used to be over here and a photon came in, and the energy of this photon was transferred to this electron that caused the electron to jump to this higher energy level. So if you take your calculator and find out the value of the difference in energy level, that is minus 3.4 minus 13.6, the value is 10.2. So this del EL. Remember these terms, everybody. So this is called the difference in energy levels. That's equal to 10.2 electron volt. And the photon that must have been coming must also have had the energy of 10.2. Energy of the photon must also be equal to 10.2 electron volts. So that's the thing, everybody. Always remember, energy of the photon is always equal to the difference in energy levels, whether the transition is for energy level rising or dropping. Energy of the photon is always equal to difference in energy level. So the question says, which of the following could not have caused this transition? So the atom absorbing a photon with an energy, we just found out the energy of the photon was 10.2 and not 13.6. Had it been 13.6, the electron would have been risen to the ionized state, as in over here. That would have been 0 electron volt. If the photon energy were 13.6, the electron would have jumped directly to this 0 electron volt level. Question 8 is actually my favorite question from this entire paper. So let's see. A battery is connected to identical uniform nichrome wires PQ and RS. A voltmeter is connected to the wires as shown. The battery has negligible internal resistance. Which of the following is the reading on the voltmeter? The answer is 2 volt, of course, and let me show you why the answer is 2 volt. So for this question, you have to have a very clear understanding of voltage drop. If you don't have a very clear understanding of what voltage drop is, I would definitely suggest you to review my lectures on voltage drop topic. So this 4 volt is shared among these two sections of this wire, and the length of this section is 0.25 meter and the length of this section is 0.75 meter. So we all know resistance is proportional to the length, and in a series circuit the voltage is shared according to the ratio of the resistance. And if you don't have the resistance, you can think of it this way, that the voltage will be shared according to the ratio of the lengths. So 0.75 is 3 times of 0.25, meaning this section of the wire has 3 times the resistance. So over here the voltage would be 3 times compared to this section. So this section and this section, when you compare these two, this section will have 3 times the voltage of this section. Now, can you think of two numbers? How to divide 4 into these two sections so that this part has the voltage and this part gets 3 times the voltage of this, and if you add them up, the value would be 4 volt. So it's fairly obvious the answer is 1 volt and 3 volt, because when you add these two voltages up, the value is 4 volt. So you might be wondering, that must be it. No, actually. Then you have the second part. In this part, the voltage will be shared exactly the same way. This part would get 3 times the voltage compared to this part, and when you add them up, the value should be equal to 4, just the opposite of what you had done previously. So this section would get 3 volt and this section would get 1 volt, this part. Now bring in the concept of voltage drop. Up to here, the voltage or the potential is 4. If this section must have a voltage drop of 1 volt, this part, at this part, the potential must be 3, because the difference between 4 and 3 is 1. And it's very obvious, if this is 3, to get a potential difference of 3 volt, over here the potential must be 0. The same thing over here, since these two wires are connected in parallel, the wire below will also get a voltage or potential difference of 4 volts. So here you have a potential of 4, and here, to give a potential difference of 3 volt, the potential over here must be 1. Again, If you feel this is a bit confusing, please go back and watch the video on voltage drop, as well as the difference between potential and potential difference. And of course, if the potential over here is 1, to give a potential difference of 1 volt, the potential here must be 0. So when you connect a voltmeter at this point and this point, look at this everybody. This point the potential is 3, and at this point the potential is 1. So what does a voltmeter measure? A voltmeter always measures the potential difference between 2 points. One of the points has a potential of 3, the other one has a potential of 1. So what's the difference between 3 and 1? Answer is 2. Question 9 says, the number of conduction electrons in a light-dependent resistor changes as light intensity increases. Which of the following best explains how the number of conduction electrons changes? Okay, what's going on? What happens is when light falls on a light-dependent resistor, electrons on the valence band jump up to the conduction band. So it decreases because lattice ions vibrate? No. It increases because lattice ions vibrate with a larger amplitude. It increases because the electrons gain energy from the photons of light. It decreases because electrons are released due to the photoelectric effect. This has nothing to do with photoelectric effect. Photoelectric effect deals with electrons being released from metal surfaces, and light dependent resistor is not a metal surface. What happens is electrons in the dark, when the light dependent resistor is in the dark, electrons are generally in the valence band, and when light intensity increases, electrons gain energy and jump to the conduction band. So the answer should be conduction electrons increases. Why? Because now the electrons are in the conduction band. So answer should be C. Question 10 says, in 1927, G.P. Thomson first demonstrated that electrons passing through a nickel crystal produce a diffraction pattern. Which of the following can be concluded from this observation? Let's focus on diffraction pattern. Diffraction is a wave phenomenon, everybody. So if electrons can undergo diffraction, it means electrons must have wave properties. So the answer should be B. Electrons behave as waves. Question 11 says, the diagram shows a ray of light incident on a glass block. Complete the diagram to show the path of the ray as it enters the block. Use the space below for any calculations. So what's given in the question? The refractive index is given. The very first thing you have to do is measure this angle of incidence. First draw normal, of course. First draw normal, then measure this angle of incidence with a protractor. Once you have this angle of incidence, you can use the refractive index to find out the angle of refraction. Once you have the angle of incidence, using the refractive index, you can find out angle of refraction using n equals sin A by sin R. So put in the values, and the value of R is 31.2. And how do you draw that in your diagram? Again, use a protractor, just like the way I have used mine over here. So the value of R is 31.2. You can round it off to 31 as well, no problem. Second part of the question says, the speed of light in a different type of glass is 1.96 times 10 to the power 8. Calculate the value of the critical angle at the boundary between this type of glass and air. So forget critical angle. Just recall refractive index. There are several ways of finding out the refractive index, and one of them is using the ratio of the speeds. So speed in this medium divided by speed in air will give us, sorry, my bad, speed in air divided by speed in this medium will give the refractive index of this type of glass. So the very first thing we do is speed in air divided by speed in glass, and refractive index is equal to, just divide these two values, and the refractive index is 1.53. Once you have refractive index, then bring in the concept of critical angle. What is critical angle? N equals 1 by sine C, and just make C the subject of the equation, and you get the value of critical angle, which is 40.8, rounded off to 2SF, you get it 41. Question 12 says, a student set up the circuit shown. The battery had a negligible internal resistance. So here you can see we have a 12 volt power supply and 3 kilovolt resistor and a thermistor are in series, and these two are in parallel with the 2 kilo ohm resistor, fixed resistor of course. So the question says, determine the milliampere reading when the temperature of the resistor is 54 degrees Celsius. So you just go to the graph and see the corresponding value of 54 degrees Celsius. So for 54 degrees Celsius, the value is around 0.98, and please check it is in kilo ohm. So what do I do first? The very first thing you do is find out the resistance of the series section. So in series you can see these two are in series, so 3 kilo ohm and 0.98 kilo ohm are in series, and these two are in parallel with the 2 kilo ohm resistor. What is your next step? Then find out the total resistance. So resistance in the series section is 3980, and this is in parallel with the 2 kilo ohm or 2000 ohm resistor. So the equation for total resistance in parallel is 1 by RT equals to 1 by R1 plus 1 by R2. So the value of RT is 1331. So I have the resistance, the total resistance of the circuit, and I also have the total voltage. So use the equation V equals to IR, put in the values. V is given in the question, 1331 the total resistance you just found out. Just make I the subject of the equation. The value is 9 times 10 to the power minus 3. So always remember 10 to the power minus 3 is milliampere, right? So the value is 9 milliampere. So for part B, the question says, explain how decreasing the temperature of the thermistor affects the voltmeter reading. Do not include calculations in your answer. So let's see where the thermistor is and where the voltmeter is. Okay, so here's the voltmeter. You have to see something, that this thermistor is in series with this 3 kilo ohm resistor. So what did the question say about temperature? Temperature is decreased. As temperature decreases, we all know the resistance of the thermistor increases. And in a series circuit, voltage is shared according to the ratio of the resistance. Since this now has a greater resistance, it will have a greater voltage, so the voltmeter reading would increase. So let's see how the mark scheme says this. As the temperature decreases, the resistance of the thermistor increases. Fairly obvious, the first point, and therefore in a series circuit, the greater the resistance, the greater the PD across the component. Therefore, the voltmeter reading increases. So the part that I have given in the bracket, you can ignore that as well in your exam. But it's better if you write this, just to stay on the safe side. Next part of the question says, explain how decreasing the temperature of the thermistor affects the power dissipated by the 2 kilo ohm resistor. Let's take a look at the 2 kilo ohm resistor. Sorry, over here. So the 2 kilo ohm resistor is in parallel with these two, right? So the 2 kilo ohm resistor will always have a voltage of 12 volt across it, right? Because in a parallel circuit, the voltage remains constant. So since 2 is in a parallel circuit, the voltage across it will remain the same. Voltage remaining same, it is a fixed resistor, meaning its resistance is also the same. So can you recall the equation that links power, voltage and resistance is P equals V square by R. Since the V is constant, R is constant, there will not be any change in the power dissipation. So let's see how the mark scheme says this. The 2 kilo ohm resistor is connected in parallel, and therefore the potential difference across it remains the same or remains constant. Therefore, as it is a fixed resistor, the resistance is also constant. Therefore, according to P equals to V square by R, the power dissipation is also the same. Question 13 says, the photograph shows a thin coil tungsten wire used in a filament light bulb. Complete the sketch graph to show how the current varies with potential difference for a filament bulb. So my suggestion is always not to memorize the shape because you will get confused. This question is IV. In your exam it might be a VI graph, so it's very easy to get confused. So always remember this phrase. When it comes to a filament bulb, always remember a large change in voltage only causes a small change in current. So the shape would look like this. A large increase in voltage only causes a small increase in current. So you know what, if it's an IV graph or a VI graph, it really doesn't matter. If you apply this concept, your answer will always be the same and right, of course. So again, one last time, a large increase in voltage only causes a small increase in current. B. The tungsten wire has a diameter and a length of the value is given. When emitting light, there is a current of 0.44 ampere in the filament and a potential difference of 140 volt across the filament. Calculate the drift velocity V of the electrons in the tungsten wire. Number of charge carrier per meter cube. This is basically the charge carrier density. It's also given. You know what, guys, whenever you come across charge carrier density, there is only one equation, that is the transport equation, I equals NAVE. Just recall this, I equals NAVE. Now you might be wondering, it's a 3-mark question. If we were to just put in the values in only one equation, it should have been a 2-mark question. So what is the 3-mark for? The 3rd mark is for finding out the area. So N is given, I is also given actually. V we have to find out, E is the charge of electron, which you know. So area is not directly given, the diameter is given. So using the diameter to find the area is what will give you the 3rd mark. Put in the equation, I is 0.44, N is 1.26 times 10 to the power 29. So look at this part, pi d square by 4. So always remember, 1 is pi r square and r equals d by 2. So you can write it in a shortcut way, as in area can be directly found out using pi d square by 4 instead of pi r square. And when do we use pi r square and when do we use pi d square by 4? When the radius is directly given, use pi r square. When the radius is not given, when the diameter is given, use pi d square by 4. V and 1.6 times 10 to the power minus 19 is the charge of an electron. From here, just make V the subject of the equation. The value is 0.013. Very simple. Let's take a look at the next part. When the potential difference across the tungsten filament is 140 volt, the current in the filament is 0.44 ampere. The table shows typical resistivity values for tungsten at different temperatures. Deduce the temperature of the filament. It's a 3-mark question, and I have a request for everybody, whoever is watching the video. Whenever you come across a question of 3 marks or above, a mathematical question of course, don't be obsessed with what the question is asking you. Just see what values you have in the question and just start working right away without thinking of the answer. So when you have voltage and current, you can easily find out the resistance using V equals IR. Make R the subject of the equation, R equals V by I. You know the value of V, you know the value of I, you can easily find out the resistance. This gets you some mark. That's why I always say, don't be obsessed with the answer, just get started. Once you have the resistance, and you can see for resistivity there is only one equation in our syllabus, that is resistance equals rho L by A. L and A, L is given, A you already found out in the previous step over here. Sorry. Area you already found out in this part of the question, B1. So what do I do next? Resistance equals to rho L by A. You just found out the resistance. L is given, A you found out in the previous question. Just make resistivity the subject of the equation. And this is the value that you get. So 9.1 times 10 to the power minus 7. 9.1 is very close to 9.04 times 10 to the power minus 7 corresponds to 2700 degrees Celsius. So that's your answer. Question 14 says, when an earthquake occurs, two types of waves travel through the earth. The two types of waves are P waves, which are longitudinal, and S waves, which are transverse. Question part A says, the velocity of P waves and S waves as they travel through the earth are related to the density of the material they are traveling through. The velocity Vp of P waves and the velocity Vs of S waves are given by the following equations, and the two equations are given, where K and G are constants for a particular material below the search surface. The density of one material is 2700 kg per meter cube. Calculate Vp and Vs in this material. I think this is one of the easiest 4-mark questions. All you have to do is just put in the values in this equation. You get the value of Vp. Same goes with Vs. Put in the values in the equation for Vs and you get the values of Vs. Here I have written the values to 4SF, but in your exam 2SF is fine. So round it off to 2SF and these are the values that you get. Next part of the question says, the earth contains layers of liquid. The value of G for liquids is 0. Explain whether S waves can travel through this liquid. So look at the equation for Vs. Vs says root over G by rho. If G is 0, 0 divided by anything is also 0. So Vs is 0. No. So it cannot travel through liquids. When G is 0, the value of V is also going to be 0. And S waves cannot travel through liquids. Part B of the question says, during a single earthquake, S waves can be produced by more than one source. If two coherent S waves meet, interference can take place. Everybody just focus on coherent. And the question says, explain what is meant by coherent. You must have seen this hundreds of times. Coherent has 2 points. One is the same frequency and the second is have a constant phase relationship. But how do you construct your answer with the proper grammar? Coherent waves have the same frequency. Coherent waves have the same frequency and a constant phase relationship. The next part says, scientists created a model to predict the effect of two coherent S waves at different distances from the source. The model predicted the amplitude of the S waves at positions A and B as shown on the diagram. Okay. The amplitude of wave at position A was 0. Focus on 0. The amplitude of the wave at position B was greater than 0. Okay. Explain why the amplitude of the waves at positions A was 0. So the two waves are coming from the two sources, and let's just focus on position A for the time being. From these two sources, two waves are traveling, and if you look at the paths of the two rays, you see that they do not travel the exact same distance. There is a difference in path lengths. In other words, there is a path difference. A path difference gives rise to a phase difference, and since the question specifically says amplitude is 0, this phase difference must be pi radian or 180 degree, causing destructive interference or destructive superposition. So let's see what the mark scheme says. There is a path difference for the waves traveling from the two sources. This path difference gives rise to a phase difference of 180 degrees, meaning the two waves are in antiphase. And when two waves being in antiphase superpose, what is the type of superposition that ensures? It's destructive superposition. Question 15 says, the diagram shows a circuit containing three identical resistors A, B and C. The cell has negligible internal resistance. Explain how measurements of current and potential difference could be used to demonstrate that charge and energy are both conserved in this circuit. Your answer should refer to resistors A, B and C. So you can clearly see I have underlined the two terms, charge and energy, and that's because you don't have to talk about either charge or energy. Well, you do, but not directly. You might be wondering, how do I start? How do I know if charge and energy are conserved? There is a layer and you have to look one layer down, and that is current is the rate of flow of charge. If current is conserved, then charge is also conserved. So you have to talk about current. And you might be wondering, okay, that makes sense, but what about energy? Recall the definition of voltage. It's the energy per unit charge. So if voltage is conserved, energy must also be conserved. So basically all you had to do was, in this question, talk about current and voltage and how they behave in series and parallel circuits. So let's take a look at the mark scheme points. Current is the rate of flow of charge. See, why did they start with this definition? Because the question asks you whether charge is conserved, and charge will only be conserved if current is conserved. So you have to start with the definition of current, which contains charge. Next point is, current is the same at all points in a series circuit. We all know current remains constant in a series circuit. Next, total current going into a junction is equal to the total current flowing out of the junction. This is actually a law. This is called Kirchhoff's law, Kirchhoff's current law. There are two laws. One is Kirchhoff's current law, one is Kirchhoff's voltage law. You don't have either in your syllabus, you don't worry about that. Just remember, total current entering a point is equal to total current leaving that point, and it's also in your fact sheet as well. What is PD? Is the energy transferred per unit charge. Instead of PD, you could have also written voltage is the energy transferred per unit charge. And we all know that voltage is shared between components in series, and at the same time voltage remains the same across components in parallel. So literally all you have to do was just talk about current and voltage and how they behave in a series and parallel circuit. But why did they confuse with charge and energy? Because that's what they do. Next part, B1 says calculate the total resistance of the circuit. Resistance of each resistor is 12.5. So when you look at the circuit, A and B are in parallel and A and B together are in series with C. So the first thing you'll have to do is find out the total resistance of the parallel section. So total resistance in parallel, we all know, is given by 1 by RT equals to 1 by R1 plus 1 by R2, and RT will be equal to 1 by answer. So I did it in one step. So the total resistance of the parallel section is 6.25, and these two are in series with the other one, the third one. So how do you find out the total resistance in series? You just add them up. So 6.25 plus 12.5 gives me 18.75, and you can run it off to 3SF as well, as in 18.8. Part 2 says the resistors are connected to a different cell with an EMF as shown. The cell has an internal resistance. Describe how a single ammeter reading can be used to determine the internal resistance of the cell. You should add to the diagram to show the position of this ammeter. So you have to find out the total current that flows out of the cell or into the cell. So you can put the ammeter anywhere, just making sure that this ammeter reads the current that is coming out of the cell or going into the cell. So you could have given the ammeter to the right side of the cell as well. That is also fine. So once I have the current, what do I do next? Just recall the equation, the final equation of internal resistance, that is EMF equals IR plus IR. So rearrange to make R the subject of the equation. Take I common. EMF by I minus R gives me the internal resistance. One more thing. What is this capital R? This capital R is the total resistance of all of these components A, B and C. The total resistance of A, B and C is equal to the capital R. It is also referred to as the load resistor. Question 16 says, a student investigated stationary waves on a stretched string. The string was attached to a vibrator and a mass m as shown. Okay, explain how stationary wave is formed on the string. So I was a bit surprised to see the marking points in this paper because they have dumbed it down like extensively. What happens is a wave is generated at the vibrator. This travels along the string, gets reflected at the pulley. The incoming wave and the reflected wave superpose to form nodes and antinodes. When do they form nodes and when do they form antinodes? When they are in phase, antinodes are formed, and when the two incoming waves are in antiphase, nodes are formed. So that's how you see a stationary wave. But for this paper, the answer was very simple. So these are the marking points. Check this out. Two waves, one from the vibrator and one reflected at the pulley. At the pulley was actually a marking point. Undergo superposition, and that's it. These are the 3 points. But my suggestion and my request would be to write down all the points associated with superposition just to stay on the safe side. Next part of the question says, the frequency of the stationary wave was 30 Hz. The distance between the vibrator and the pulley was 3.6 meter. Okay. Point R is 0.6 meter from the pulley as shown. Determine whether there was a node at point R. Mass is given, mass per unit length is also given. So again, in the previous questions, I also requested everybody to whenever you see a question of 3 marks and above, please don't look for the answer. You see what are the points, what are the values given in the question, you just get started. Let's say when you see mass per unit length, what equation pops up in your head? There is only one equation that contains mass per unit length, and that is V equals to root over T by mu. So let's write that down. And where will I get this T? The weight of this mass, capital M, is going to give me the T. And mu is also given in the question. So you put in the values, you get V as 36 meter per second. And don't get stuck here. See, this is how the answer guides you. I mean, the steps guides you towards your answer. Once you have V and the frequency is given in the question, what can you do? Find out the wavelength. You know V, you know F. So what is the equation? V equals F lambda. And make lambda the subject of the equation. That is 1.2. Now focus on the question. The question says whether R is a node or an antinode. So let's see. The wavelength is 1.2 meter and half of the wavelength is 0.6. So let's say if I draw a standing wave like this, if the entire length of this wavelength is 1.2, so half of it is 0.6 and half of it is at R. So R must be a node. There is a node at the pulley. Therefore R, the distance from the pulley is equal to lambda by 2, meaning there is again a node at R as well. Part C says the mass M was changed and the frequency of the vibrator was adjusted so that a different stationary wave formed on the string. Adjacent nodes were separated by 0.4 meter. Okay. The diagram shows 2 points S and T on the string at the instant when the string was straight. Explain the phase relationship between point S and T. So if you draw a standing wave like this, you'll see S is in one loop, T is in another loop, and there is a node in the middle. Always remember, particles on either side of a node are always in antiphase, meaning particles on two adjacent nodes are always in antiphase. So S and T are in antiphase. Question says explain. Look at the common word in the question as well. Explain. So when you say S and T are in antiphase, you have to justify why are S and T in antiphase, because they are in adjacent loops. Next question says explain how the amplitude of vibration of the string at point S compares with the amplitude of vibration of the string at point T. It's clear from the diagram that S is at an antinode but T is not, and we all know that displacement is maximum at the antinodes. So S has a higher or greater displacement than T. Why? Because S is at an antinode but T is not. S has a greater amplitude than T. Again, the question says explain. So you have to justify why does S have a greater amplitude than T? Because S is at an antinode but T is not. Question 17 says ultraviolet light is incident on a zinc plate. If the photon energy is greater than the work function of the zinc, electrons are released. State what is meant by work function. Always remember, work function is the minimum energy required to release an electron from the surface of a metal. Part B is really interesting. The ultraviolet UV section of the electromagnetic spectrum can be split into three parts known as UVA, UVB and UVC. The range of wavelengths of these parts is given in the table. The minimum de Broglie wavelength of the released electrons is given. Deduce whether the ultraviolet light incident upon the zinc plate is UVA, B or C. Work function of zinc is given. I have to start somewhere, and I always say when you have a question of above 3 mark, it's not a good idea to look for the answer. It's always a good idea to get started with whatever information is given to you in the question. So you can clearly see I have underlined de Broglie wavelength. So what is the equation for de Broglie wavelength? Lambda equals h by p. And if I make p the subject, which is the momentum, there is h by lambda. The value of h we all know, and lambda is given in the question, de Broglie wavelength. So this is the value for the momentum of the released electrons. Once you have momentum, you can find out the velocity using P equals mv. And once you have found out the velocity, you can easily find out the kinetic energy using half mv squared. So what do I do next? Work function of zinc is given. Do you remember the full equation for photoelectric effect? That is, energy of the photon is equal to work function plus kinetic energy. You have already found out this kinetic energy, and guess what? The work function is already given in the question. So photon energy is given by the sum of work function and kinetic energy. You just found out the kinetic energy and the work function is given in the question. You add them up, you get the energy of the photon. But guess what? That's not what the question is asking for. Question is asking you to find out the wavelength, because I have to check if my wavelength falls within the range of this UVA, B or C. So what is the equation that links energy of a photon with wavelength? Is E equals hc by lambda. So make lambda the subject of the equation after you have found out the energy of the photon, and you have 250 times 10 to the power 9 minus 9. Always remember 10 to the power minus 9 is nanometer. So the value of your lambda comes down to 250 nanometer, and you check in the range. So 250 falls within 200 and 280, so therefore it must be UVC. Part C says a student used zinc plate and UV light from different frequencies in an experiment. The student's graph of maximum kinetic energy of the released electrons against the frequency of incident UV light is shown. Einstein's photoelectric equation applies to this equation, and the equation is given. Describe two ways that this graph is not consistent with the values known for zinc plate. Your answer should include calculations. Forget everything, clear your mind. Just look at the graph and say, the question says, describe two ways the graph is not consistent. So first things first, it's a graph of kinetic energy against frequency. You have seen this in my lecture as well as in the fact sheet. So what does kinetic energy against frequency graph give us? Two things actually. One would be the threshold frequency is given here, right? The value is around 7.5, right? The value is between 7 and 8, so it must be 7.5. So I know the threshold frequency. So what can you find out from threshold frequency? We all know when the frequency of light is equal to the threshold frequency, the energy of the photon is equal to the work function. And using this value of threshold frequency, as in 7.5 times 10 to the power minus 10 to the power 14, I can find out the threshold frequency, and using this value of threshold frequency, I can find out the energy of the photon, and that will be equal to the work function. And once I have done that, I can check whether my value of work function matches with the work function of zinc. If it matches, then there wouldn't have been a problem, but you'll see that it doesn't match, and that is one of the ways the graph is not consistent. Step 1. Let's move on to the next step. Please remember, what does the gradient of this graph give us? The gradient of this graph gives us the Planck's constant. So you take change in y-axis divided by change in x-axis, and the value that you get should have been equal to the Planck's constant. But when you do the calculation, you'll see it's not. Let me show you how I have done it. At the threshold frequency, photon energy is equal to the work function. So energy of the photon equals to phi only when the frequency is equal to the threshold frequency, right? So using the value of the threshold frequency given in the question, I can easily find out the energy of the photon. And guess what? This energy will be equal to the work function. And putting in the values, I get 3.1. But guess what? The work function of zinc is given in the question as in 4.3. So do the two values match? It doesn't. Therefore, this is one of the ways the graph is not consistent. The work function of zinc is 4.3, but the work function from the graph is 3.1. So that's one of the ways it is not consistent. Guess what? The next step is to find out the gradient. Gradient of the graph, change in y-axis divided by change in x-axis. So a gradient of kinetic energy against frequency graph always gives me the Planck's constant. But look at this value, everybody. It's 2.13 times 10 to the power minus 33. Is this the value of Planck's constant? It's not. Planck's constant is 6.63 times 10 to the power minus 34 joule second. The gradient of the graph is supposed to give the Planck's constant but does not. So that is the second way it is not consistent.